Good afternoon, YouTubers. Recently, I have had many questions about how to install solar system in general. Many questions coming like how I combine the regulation with computational fluid dynamics and where my numbers, how I show up the numbers that I did on some of my Excel files. It's very important that we understand what we're doing in general. And the solar system that I'm, always talk about is sort of similar to this one shown here. Pretty much three solar panels like these in this form, and the angle of attack uh, looks more like an airplane wing, and the south is this way. So this is the north, because that's the winds that really worries me. Is the one coming from the north that are trying to make my solar panel looks more like an airplane wing. One important aspect that some people have asked me is the type of anchoring that I have. And here I'm showing you kind of a quick picture of what they looks like. It's one bolt and a wedge bolt here. I will talk about this a little bit later. One bolt here anchoring the whole thing, so it's bolted. So showing here, trying to show here that it's bolted. This might not resist too much moment. So there might be a moment, this will bend. So the moment here will be pretty much zero, basically. But there could be a lot of bending moment right here at the top, you know, creating sort of like a swaying the whole system. Well, here I'm showing you. This is a map of actually of Puerto Rico. It's being shown here, and this was Hurricane Maria. Several uh, the huge, humongous size compared with Puerto Rico, and we got very devastating winds. Just to say the least, I have shown this before in many other places. Winds 155 miles an hour. Uh, this is the solar system that I always talk about it. This is how I install them. As you can see, pretty much there's very little. South is this way. There's pretty much no angle of attack going south. And this is the story. Uh, a lot of people get a little bit confused about how I went through this. So I would say this is the third video on this series. The first one was about the how to produce this kind of table, which is the ASCE 710, and the theory behind it. But then I add this second part, theory of wind forces, like airplane winds. And I'm not going to talk today about all this because this was talked before. The 180 comes straight from the recommendation from the 710, but it's important that you get this pressure, and that pressure is this one here. When you get that pressure, at least people that have used this table before, they don't complain about it. They get right the pressure that they want. Now, here is where there's a departure that we need to clearly understand where we're going. When you get the pressure here, then you have to get the corrected airspeed because you're going to change for CFD, Computational Fluid Dynamics. And this pressure is produced by this type of wind. All right? If you are talking about CFD, this is the corrected wind speed that we are talking now to get that pressure. All right? When you get this wind speed, then you have to fire any software that will do computational fluid dynamics, like SolidWorks. It's pretty good. It takes a while. It's kind of I would say it has a very steep learning curve just to get it to work where you want it. Even for the expert, it takes a while. It'll take a lot of setting before you start to get good numbers out of it. I did it once at 30 degrees because somebody asked me to do that work before. I come out with this coefficient of drag and this coefficient of lift. All right? And that's based on this angle, 30 degrees. You can change the angle. This coefficient of lift and drag will change. The nice things, and here's a departure from my first video. On my first video, I use what is called projected area, MESI. at the end, I didn't like it. I switched to what I know best, which is wind theory. In wind theory, you use your, well, the wind area, which is basically the core by the length. And I see here is a wind, or whatever you want to see it. But I see a wind coming from this. I mean, wind coming this way are trying to make this like an airplane wing, okay? And so our job is to ensure that that will not happen, that they stay anchored properly the way shown here. So I switch from my first video to my second video. The second video was about CFD. I switched to then to regular area, the one that you can easily measure by the core and the length. It would not matter the angle. It will stay the same. And that's a big difference between my first video and the second video, because these coefficients are evaluated according to what area you're talking about. Okay, in my first video they were based on projected area. On my second video, and this being the third one, are based on the core and the length. That's it, right? That's no more to that. If you do that, like for example, if this 16.5 is about 3 solar panel, the way it's shown here, and 3.3 is the core here. That gives you a total area of 53 feet square. That's it. Now, with this angle and using SolidWorks to do the CFD, Computational Fluid Dynamics, you get this value. When you get this value, then you get the force of drag and the force of lift. The force of drag is basically you take the pressure, you multiply by the area, and then you multiply that by, for example, the coefficient of drag, and you get this. Well, actually, this is not in Excel. This is a still photo, but we go through Excel in a second and we'll see it. You get then the coefficient of the force of drag. And the force of lift is the same. Not a big deal. So these are the actual forces coming that are trying to make these look like more like an airplane wing. All right, let's go to actual Excel. Let's see if I can open this. And there we go. So you can see 3 simple calculations. Is C10, which is the pressure, by C15, which is the total area, by C18, which is in this case the drag, 0.6, and that gives you the force of drag of 1328 pounds. How about the force of lift? It's the same story. That's the nice things when you define the coefficient of lift and coefficient of drag on the surface of your solar panel and not on projected area, which is crazy. So going back, eventually this number direct to calculate the actual, the net force over my solar panel, and based on the total solar area, it gives me a total pressure of about 45, not far away from where I start with, 45 pounds per square foot. Not a big deal. But remember, your solar panel should have to resist, this kind of pressure. Otherwise, we'd be in trouble. Now, the calculation that follows here depend on your type of model anchoring structure. See other videos on the subject. Well, actually, I don't think that there's any other videos on the subject. I thought to, put that together and end up being this one. This one will have a little bit about this story that I thought to put it in a video, but as you know, time is a little bit complicated lately. So eventually, if you do the math and forget about, that this here is anchored by a bolt. So the only forces that you need to worry, for example, is on the in the y direction. Then that total force is about 1300. You can see here the amount of all the calculations you have to do to get that right, and by difference, then you get the other force on the other side that need to add all this lift force. All right, the lift force. So that would be 652. Then, what's next? Well, this force is distributed within this 3 bolts here and the other 3 bolts on the other side, so you can basically divide by 3, and that's what you have divide by 3 here. So that end up being in one side, like for example on this size, on the, let's put this here on this side, then the force per volt will be about 450, and the force per volt on this side will be at 217, way below the maximum. uh, and the maximum actually is a little bit higher than the one that I'm posting here. I think the maximum I will show you, but it's about 100 625, I believe. I will change this. It's about 165. There we go. So, and that's when you anchor 1 volt, you get this amount of force. So you are definitely, you are covered, right? If you do this type of anchoring based on the calculation that I'm talking about here. So when you get this number, the force of drag and the force of lift, I will definitely recommend you to move then to your another software to do that calculation, which I will show you later on. Let's see if there's anything here that I need to stress. I'm going back here, and there's issues. Like for example, I did a solid 30 degrees. How about if you change the angle? Well, you change the angle, the coefficient of lift and drag will change, period. And you will have to calculate them because there's no way around. You have to calculate them. However, you can use SolidWorks. I mean, you really want to use SolidWorks, you can definitely and get the results that you want. It take a while. It take a while. It's hard. I would say it's kind of hard, but I mean, when you get used to it, no problem. It has a very steep learning curve, I would say. It's not that straightforward. Like you do this and that, and you order solid and get the numbers. Fusion 360 for doing this. Fusion 360, as far as I know, will not do CFD. It is a pity because Fusion 360, the learning curve is much smoother. I mean, you can learn a lot of stuff in Fusion 360 with few hours in a day. SolidWorks will take some solid work for you, for your part, to get it to where you want it. But I mean, definitely, it's a great software, very good software as well. But I, today I have an alternative for you that you don't have to use SolidWorks to get the coefficient of lift and drag. I will show you that later on. We make life easier, a lot easier. Again, here I'm using how to calculate lift and drag coefficient based on solar panel angle using CFD in SolidWorks. This is part of SolidWorks that I did. Some of my work done on that at the 30 degrees. This is how I anchor my system, and I'm showing you what I have done, which is based on an angle of 2 beams of an angle of 2 inches by 2 inches, and the thickness of these guys is about 1/8 of an inch. All right, I will tell you a little bit more. Let's see if I have anything else. Nope. This is the type of anchor that I use. Wedge anchor 3/8, and that's what I want to use. That's what I'm using right now in my system. And so this is 1620 actually, the force allow it. Now on shear, let's see, let's go back here 1 second. Shear force, let's see, tension and shear value. Here is the shear nearby. You see I'm right here. 1 volt is about almost twice the shear force, because I'm going to be on this line, on this top line. That's my 3/8. Here we are, 1620 on the tension, which is pull out force, and 2300 on the shear. Shear never is a problem, not at least for my case. All right, that will do. Let's see, anything else that I need to show here? Well, that's basically it. Now, the next part I'm gonna show you is how to get the different lift and drag coefficient using a very, I would say, elegant software to do that, and it's for free. So you are invited to take a look at it, and in case you have a different angle that you want to tackle on your project. I also combine that with another software which is called F-Tool. Excellent software to for beam analysis. So with that said, let's do that. Oh well, here we are back again. Now, the idea of this code, this software from NASA. This is interesting, huh? We are talking about solar panel, and all of a sudden we are right here with NASA. Well, what happened is we are talking about coefficient of drag and coefficient of lift, and I think NASA knows a little bit about that and make life easier to understand what will happen to our solar panel when you put that particular solar panel to a given angle, and the wind is coming, as I always said, from the north. So then what we actually have is just a wind, an airplane wind. Now, what type of airplane do we have? Well, you can pick from any value here, like airfoil, ellipse. How about a plate? A plate seems more likely like a solar panel. And the nice thing is that you can change the angle, and you can see how the number quickly changed to something. Now I will explain that in a second. Like if you put your angles like these, and all of a sudden you have a Formula One spoiler, the spoiler at the back, and depending on how much area you have on that spoiler, then how much downforce you will have on your car. Well, that's not the case. We have an angle, but it's always like this. I think that the maximum that this software has is about, this is again foil sim. It's called airfoil simulator. Basically, that's what it means too. And 20 degrees sounds okay, mostly for all the work that we do. Now, if you happen to be very north in USA, then this would not work for you. But then you will have to use, like for example, SolidWorks to get the proper coefficient of lift and drag, which are very important for the calculation that we are talking about. And again, the idea is that I can change accordingly of what I need. Like for example, a plate at a given angle, let's say 20 degrees. Now, what will happen? Let's put the size of that plate. So what I will do is adjust that plate according to my solar panel spec, which is about, the core is about 3.3. There we go, 3.3. And the span is about 16.5. You can move this to make it faster, sometimes a little bit. Okay, so that's gonna be 16.5. Oops, that will do. An aspect ratio of 5. Good. So I got that. Flight. What will be the speed? The only bad here is that my setup on my screen looks kind of crummy here, but don't worry about it. Gonna leave that the way it is, not change much. Altitude, 0 altitude sounds okay. I'm not in any elevation where I'm located, but if you are, you can change it, adjust it. Now, the speed. This speed is the actual speed after you come out with after application of, let's say, of your ASCE 710. The speed that you will use at the end of all that is not the 180 as stated by the code. The 180 is just to get the pressure, this pressure here, the 40.5. When you get that pressure, you have to, come out with the corrected airspeed for doing what I will call CFD, Computational Fluid Dynamics. And this is the actual speed, 125, 126. That's pretty much where it is. And with that, then, and the angle, the 30 degree here I use this one from SolidWorks, but I'm not using SolidWorks. And at this point, the issue is it takes me a little while to adjust that 30 degrees to anything else and then calculate the coefficients of lift, like for example here, and drag. And it takes me a while. I mean, it's not that easy using SolidWorks. It take a little bit of effort, and that's when you understand SolidWorks. If you don't, you have never used SolidWorks, then it's gonna take you a while to really get it. Now, using the simulator, for example, going back to the simulator here, life is easier because it's just, it has this kind of bar. You adjust whatever you have to adjust, and you are right on. Like for example, how about adjusting the 125? That's the actual speed. I think that's 125. Actually, let's see what's the actual number. 125.8. So we use that one. 125.8. That's it. Now with that, you start to see the force caused by this coefficient of lift and the drag caused by this force here by this coefficient. If you remember, the 30 degrees is a higher inclination, and the coefficient of lift is a little bit lower than the 0.99, and the coefficient of drag is higher, meaning that I have this force is a lot bigger. So you can quickly see that if I change the angle of attack, thinking more like you are dealing with an airplane wing. Like for example, let's see, flight shape. If I reduce from 20, let's say, to 15, you start to see some of the numbers changing. The coefficient of drag is going through. What is interesting is that there's a maximum. If I reduce the angle, you might experience a larger lift force as shown here. And let's say, oops, there. I'm going back to a flat plate, and so you can see 277 is getting bigger, 2783, 127, 2800. The numbers keep increasing. I'm going slowly so you can see that. On the other hand, the drag is coming down, but the lift is going through a maximum. 280, 20. That's it. I think that's basically it. So the maximum coefficient of lift is about 128. Anything above that, anything, if the angle goes higher than that, it tend to, I would say, this value get reduced. However, this start to increase very quickly. So you can really start to generate your own data of where are your plate with respect to the angle and what are the forces based on only on coefficient of lift, coefficient of drag, but very important also that is based on the actual area of your solar panel. You can punch here your solar panel area, and you are, pretty much on your own. You come out with your calculation. Let's see, anything else here that is important? I think so. I think that we are in good shape. Geometry, well, that's, you want to translate all these forces and so forth into the geometry of your wing data. This is good. Data, now you have all the numbers, and where the actual speed 125, and here's the lift and drag based on this coefficient of drag here, 2.237, and the coefficient of lift. If I'm going back to Excel, the one that I did, you see the coefficient of lift was lower, but the coefficient of drag was it's about almost 3 times the coefficient of drag at because I'm a higher angle here. This is 0.92. So the force of lift here is about, on this solar panel, end up being about 2001, and force of drag 1328, and because it's at 30 degrees. I mean, remember, it's at 30 degrees. I'm going back again to my solar panel, and here I'm at maximum 128. So it's kind of nice. I would say that you can, play around with this, get the forces, the actual forces, and but again, to do that, you have to deal with the regulation just to calculate this, the actual speed based on this guideline and this theory about wind loading as per ASCE 710. There's more recent one, it's 716. I haven't go through that, in all the details, but again, this is where you get this maximum. The 180 is where you get it from there, and from there I get the pressure, and when I get the pressure, then I get the corrected airspeed for to do computational fluid dynamics, or CFD. When you get the CFD, then you get the proper, in this case, the coefficient of drag and the coefficient of lift. When you get these two, then you get the forces. Straightforward, no big deal. You take the pressure, multiply by the area. Where's the area? Right here. The total area, these two numbers, and then multiply that by the coefficient of drag, so you get the force of drag, or the coefficient of lift, and then you get the force, in this case, of lift, which are these two numbers. It's very important that you understand where these two numbers come from. There are people that get all messed up, and if you don't have the right unit, for example, you try to use the density of air, like 0.07 pounds per cubic foot. The unit there, you have to divide that number by 32 to get it into slug, SLUG. So be careful with that. Now, by saying that, then the next part is these forces. Some people get all messed up with these two forces here, and these forces are based on the fact that what will happen if I don't have any bending moment whatsoever at the anchor point here. What will be those forces to keep this within place? There's a long story behind this number, but as you can see, I kind of pounded so people will know what they are. And so this one is just the difference because they will balance out. Anyway, so the story is it heavily depends on what you're doing here. So be careful with the type of how you're going to anchor your solar panel. So going back to your CFD using foil sim, and the version that I'm running right now, this run from actually this is running from the NASA webpage, so you can use that one. And so what I was saying is kind of nice, like for example, let's see, shape. I think that we are okay there, nothing more to say there. Flight, should I change anything on flight? Nope. Analysis looks good. 2D view, 3D view. Let's see. You want to be sure that you follow what your kind of airplane wing looks like. I keep the 2D view. Now let's see size. I think that we have about here size. I think that we went through all that. Here is something that I need to change. You want to be careful when you change something, because sometimes it changes something else. Like there's a dependency on some of these numbers. There we and I need to go back to what is 3.3. Yeah, 16.5. That's perfect. That's about 54. And the aspect ratio that I'm using is 5. So I don't want to change that. I think geometry, data, plot. Still missing one aspect here. Let's see if I select plot maybe. Analysis. Oh, there we go. It's an analysis. I want to show you. That's kind of neat. So you see what's really happening here at the tip of your solar panel. So you can see where the force and lift are coming. And this is kind of nice. The first one I had was streamline and moving, which is kind of nice. Oh well, looks like we got, you can do, I mean, when you have the area size, when you have the proper area, here we go again, it changed what did I change this? 3.3 actually, 3.3. And this one was 16, nothing else to change. There we go. Now gauges again here, good. I think that we are in good shape now. Finally. Now going back, oops, I have here a problem. You can see it's changed me the shape. Let me change the shape again. It was a flat plate. And now you see how this lift and drag coefficient change accordingly. So I'm right at the 20. Any, you know, when if there's a big, an issue here, you always can print your results and see what's going on. Like for example here, I got the area, the score 3.3, the span, so good. Everything looks good. Density in this slack unit per cubic foot, pressure good, speed, that's everything look good. Let's see if I can drop a little bit more into this. Yep, now it looks good. So that's what I have. So if you change the area of your solar panel, then you're gonna get these lift and drag forces based on this coefficient of lift and coefficient of drag. So as I said, you can change the angle of attack and watch, let's say 10 degrees. That's typical for Puerto Rico. You know, about to 18, I would say. More typical is about 18. Everybody adjusts pretty much the solar panel at 18 degrees in Puerto Rico. I don't do that. I'd rather lose a little bit of efficiency than losing my solar panels to strong winds. Unless you have your panel well protected on, you know, through either you have parapets long enough that protect the north side of your solar panel, that will do. But again, looking here, so you can see the forces here. The idea is that when you get those forces, then is what you have to do is go to your favorite, I don't know, let's say, like for example, this one here. Right here, I mean, what is called a two-dimensional frame analysis tool. You can do some of this by hand. I don't like it by doing by hand. Take a while. I'd rather use like a very simple software. This take about 10 or 15 minutes to set it up, and you start to get good numbers. Like for example, I'm here with this number, the 1.328. Actually, let's open this big. Here we go. These numbers come from the 30 degrees angle. So I have this frame set at 30 degrees, and that's the important part. So you take the degree here, this from this horizontal line, you got about 30 degrees here, a little bit more or less, because I'm using this unit 1.5. So it's about here. You subtract this, so I will give you 1 foot, and through this 3.26 for the hypotenuse, and you get the angle. So it's about, I would say, 31 or so, but not bad, close. Now these forces here are the one we're talking about. When you go through this software, which is F-Tool, it's called F-Tool. I think it's a Brazilian software, but it's kind of nice. I like this a lot better for doing this kind of job than any other more complicated software for doing beam analysis. I love this. It's so straightforward. You only have to set, like for example, the material. Select the material. I call it solar panel here, but the material is just aluminum and isotropic aluminum. Then you establish the dimension what you're using. I'm using an angle type of beam, which are 2 by 2 by 1/8 of an inch. So you do all the calculation for me. Then I choose the type of how I'm gonna anchor my solar panel. Uh, Basically, you have what I'm showing here is like a side view of what I have, but the forces are the full forces. So these, you have 3 of these and 3 of these spread, on this axis going down. So like this 1, 2, 3. You see, coming down. So this is what is very typical design here in Puerto Rico to accommodate your solar panel on this fashion. So just to avoid too much exposure to wind from the north coming this way, because this obviously the solar panel are directed to the south. Here's the sun shining heavily on your solar panel, but the wind coming this side will try to make your solar panel look like airplane wings, and that's not good. So going back to F2, so in F2 you have when you set the dimension of what you are setting, then the only thing that you need to do is watch the numbers coming out. Like for example, one thing that I discovered very quickly is that there was too much bending force here at the top here, and all this is bending forces. So let me see how this looks like. Oh, that's bending forces, but let me go back to this one, and that told me that although I mean that much bending will happen, up to here, you're gonna get about 0.4 of an inch. 0.4 on an inch might not be much, but it might be significant. I mean, it's bending. I mean, when you expose these, the way I set up, and how it's set up, this is bolted. This is bolted here, so you have basically, as shown here, on the. Let me go back here for 1 second, and let's see if I can make this. 1 second here until I fix this. There we go. There we go. Let's see what I got here. It's showing somehow it's not showing the actual. It's showing like free, and that's not true. Somehow, you see. Let me put that. Let me check that out. It's showing something here. You can change it, but that's not my actual design. The 3 of them are free. The only one that is free, this is fixed, and this is fixed. And when you select that point, I can select this point as well. So I got selected those 2 points, and that's when you set apply. You see, it will not change because that's the way they are. Somehow, let's see now. Well, it will stay the way it is. So they are bolted, and that's what I'm using. My design, when I put this together, this was like this. However, there are some people that have, commented to me that they will do these will be on a fixed mode. Everything will be fixed. You fix the 3 of them. Watch this how it change. See, if this beam or this column is anchored here, and I can do this, the number will change. I mean, we have a totally different analysis. Let's do this one with that in mind. So you watch what's going on, because I think it's important that you understand the difference between when you bolt and you anchor this way. Now, if I do this now the way it should be, like for example, let's check the moment. You see, this is a big deal. We have a problem in Houston. We have a lot of bending moment right at the anchor points. No good. This is so huge that we'll pull this bolt out of the socket here. So that's a problem. We cannot allow that to happen, and therefore this is not a good design. at least for my case, for what I'm looking. If I anchor like this, I'm gonna be in trouble with this amount of about almost 600 feet. Remember, this is kip, but this is then in pound, will be 600 pound per foot. And this is about 800 pound per foot right here. Not good, not good. That's a problem. To reduce that amount of moment, you can certainly do, if you want to anchor this like this, rock solid, you have to reduce this bending moment right here. One thing that you could certainly do, let me go back here for 1 second and let me is to include you need to brace this frame. So to do that bracing, you will have to add a line here, like for example, do that from here to here. I did that. Now before you do anything, now you got to go back to all the properties, because that's a new so you got to go back here and said, well, we want to apply solar panel material to that particular beam for doing the bracing, and I can certainly do that, but then I need to check these. We are good to go. We can always check, like for example, let's see what's the property here, and I did a right click. Yeah, isotropic. Yeah, that's aluminum. Properties, and this is the dimension. Look good. How about this one? Right click, everything the same. You want to be sure that everybody's was picked right correctly. And this last one. Good. So let's do that now. Let's do a check. What will be the forces back again? So I do again a bending moment analysis, and you can see how the value, this moment value, dropped to almost nothing. They are in zero right now. 0.44, 1, 2, 3, about 44 pounds. And this is about, let's see, this is on the bracing, but the value here, this one here, is point. Let's see if I can take some of this value out because it's getting harder. A little bit difficult to read it. There we go. This one could be dropped more. It's a little bit large, but you can take the bracing line and getting a little bit higher here somewhere, and from here, let's say to here, so you can reduce that even more than what it is, but it looks a lot better than it used to be, just because I did this bracing here. So it definitely helped a lot our system. So again, going back to what we need to do, let's see where we are right now. Let me see something here. Okay, you can do as well how much you move per liter. I mean, you can step here and see that the numbers are almost like 0.404. It's almost nothing. Nothing to worry about. How about here? 10 to the -1. Yeah, very little. And this one belongs to the solar panel. So again, let's see here. Nothing that I need to worry about. Good. I would say that this is the only one that bothers me a little bit. It's a little bit high, on the high side. So, but again, you can drop that. If you increase this line somewhere here, it might do better. But then you have to add another point here and do a little bit of more work. But for me, since I'm not working at 30 degrees, these forces are so small that I don't have to deal with them at all. Now, let's see where we are now. I think that that's more than enough that I want to talk about it. Remember, it's important that you understand how you anchor your system. This is a rock solid anchor, and versus if you are using bolt. I use bolt. It's like, for example, you don't remember how I used to do that. This is what I did. I step here. Actually, before I doing that, so you check here, and I step here, and I also step here. So I choose how I'm gonna anchor this, and I said you are gonna be fixed, you're gonna be fixed, but you're gonna be free to rotate. So that means that this beam can rotate freely because it's a bolt. Now this will change, the whole thing will change. So I will say apply that, and there we go. Now if you do now all the other study, oops, continue. Let's see. Okay, sorry for that. I haven't set the forces. Now they are right where they're supposed to be. And so there we go. Shear forces, bending forces. Obviously, there's no bending moment right at the bolt. Only the forces that are pull-out forces. Like for example, I need a 1.4. This is very small value. Remember, this has to be divided by 3. So it's 1/3 of this. Now going back, let's see how this looks like. There's a lot of bending here, bending moment 679. But then the question is, would that be a problem? Check this out. Nope. It would not even move. It would not bulge. Maybe here a little bit, times 10 to the minus 1, not a big deal, you see, times 10 to the minus 1. Everything looks good because I put this right here. You brace them. Again, this is at 30 degrees. If I show you photograph of my system, I didn't brace them at all, just because the forces that I'm dealing with are so small, you know, that I don't have to deal with all that. But I'm showing you, be careful what you're doing. I mean, again, I have received many questions about anchoring solar panels, and it's kind of hard to go through all that details, except that I can show you what are the tools available to make your life easier for if you want to tackle your own project. And again, I will start watching the video number 1 about how to get, in this case, all these parameters, where they come from. They're very straightforward. It's not this. I mean, this is like a recipe. Like you are cooking too much oil, this amount of oil, this amount of salt, this amount of sugar, this amount of that, and so forth. So you go through that and get that. You shouldn't have any issue to arrive here to what's the pressure in your solar panel. When you do that, then here is when I switch to CFD, Computational Fluid Dynamics, and I obtain the actual airspeed for my solar panel. When I got that number, then this number I punch it in any CFD simulator like SolidWorks or simulator from NASA, the simulator that for solar panel. It's not a solar panel. It's a plate. It's a plate at a given angle. You know, like emulating a wing, an airplane wing. So when you get that, then eventually you're gonna get the coefficient of drag, the coefficient of lift, and based on the area, the total solar panel area, then you get these two numbers, the force of drag and the lift force. This is pound. let me drop this 1 second, so I want to be sure that you understand some of these numbers where they're coming. So I'm showing you both at the same time, so I'm not goofing here doing this right. You see this number 1.328, because this is skip 1,000 pounds, 1.328, and 2 the force of lift, that's what the 2.001s right here, and the force of drag is right here. See, and that forces eventually this software F tool, which is a two-dimensional frame analysis tool. It's great. Let's see, let's check something here. Option display, options. I'm looking about F tool. There we go. Oh, I see. Yeah, I remember. Yeah, I knew that was from Brazil, and this is I definitely want to give credit to whoever developed this, which is Mr. Luis Fernando Marta. It really saved a lot of time when doing a small beam calculation. This is so straightforward. This guy deserves at least a medal. You know, he did a marvelous job. So straightforward to do this calculation, and definitely marvelous job, Department of Civil Engineer, and excellent job from Mr. Luis Fernando. And it's a free software. Get it and use it. It's pretty much self-explained itself what you need to do, and there's many examples around. So this is definitely a lot easier than SolidWorks. SolidWorks takes some solid work on it, to get it where you want it. But no F2. F2 is nice, very nice. You just need to understand what you're doing a little bit, and particularly like these things, like how you are anchoring your system. When you do that, it is straightforward to start to get good data from this system. Again, so when you do that, then you start to get these forces here. Now, if I go a little bit below here, you see I got this force here, which is basically this number here. And I also got this number here, which is basically this number here, the 608. These numbers are, remember, this is based on, I think that the degree here is about 31 degrees. This is actually 30 degrees. This is true 30 degrees. As you check out here, that what is inside, let's see. That's the formula. There's a long formula there that depends on the many parameters that are around it there. So that, again, that gives you that number. But this number here are based on the two-dimensional analysis of these beams. But it's kind of nice that it come out pretty much the way it should be. Now here, the nice thing is you also have the shear forces. And so, we can talk a little bit more about shear forces and these pull-out forces. The only important part here is, remember, this number has to be divided by 3, and so this one. So you divide this by 3, this by 3, and you will realize that you are definitely well in the safe zone. Like for this force, like force per bolt is about 450, and the force per bolt on the other side is about 217. And what else we got? And remember, this have nothing to do with shear here, but shear is pretty much guaranteed. That shouldn't be a problem with shear. But it's this pull-out force is the one that worries me a lot. Now, for the 3A bolt, the maximum shear force is a little bit higher than this value here, but it's okay. Basically, we are in good shape. 6 total bolt in anchor for a total force of 10,000. So we are above this value here with now. In terms of pull-out force. If I go to shears again, let's see if I go to shear for a second here. Here is you can pull through bolt wedge anchor technical data. This is the bolt that I'm using from concrete. Basically, 3/8 of an inch, and I'm using 1.5. I'm using this, so that gives me on a 2000 psi concrete a pull-out force of 1600 per ball. So that's a good number for me. That's the number that I took for my design. A little bit more data onto this. This is how I went into it. My slab is about 4 inches, so that's why I embedded to about 1 3/4 of an inch for my 3/8 of a anchor bolt, and that gives me this amount of pull-out force, 1600 pound, which is more for what I need. I think that I have covered pretty much everything that I want to say about all this. If there's an order of how I install things around or do the calculation, ensure that you start by here. Just start by using your calculation from the ASCE 710. Do this bunch of parameters, get the pressure, from the pressure get the corrected air, from the corrected air get the coefficient of lift half drag, get the forces. Then when you get the forces, then decide what type of anchor you will have, because depending on the type of anchor that you have, things will change accordingly. Like for example, I'm showing you here, you can have this type of anchor with bolts, or it's going to be rock solid. And when you have rock solid, there's a lot of moment developed here that you have to worry about them as well. But if you put this brace, your design, it will reduce the forces that you have to deal with them here. So you need to brace your anchoring system to avoid bending, which that's the bad part. Oh well, I think I'm finally obviously using this guy. You can definitely use this guy. I mean, from NASA foil simulator, and if you are working up to, the only bad thing is that it only works up to about 20 degrees, and that's the only bad part, I would say. Anything else? Nope. That's basically it. As I always said, be safe, whatever be your final destination. Bye.